This presentation will focus on the alleged physiopathology of the pH variation in the setting of metabolic acidosis, either due to bicarbonate consumption or due to bicarbonate loss. Let's start with metabolic acidosis due to bicarbonate consumption. In this simplified model, a strong acid will be added to the plasma, causing an upheaval in the elements printed as table headers. Notice that the pH is expressed in units, the pCO2 is expressed in millimeters of mercury. Bicarbonate, carbonic acid, sodium ion, and chloride ion concentrations are expressed in milliequivalents per liter. When the concentration of H+, i.e., hydrogen ion, is marked with an asterisk, it is expressed in nanoequivalents per liter. Otherwise, it is expressed in milliequivalents per liter. The strong acid will have a plasma concentration of 20 milliequivalents per liter, and will completely dissociate into protons and the unmeasured conjugated anions B. If unbalanced by the carbonic acid bicarbonate system buffer, this will lead to a dramatic drop in pH, which will fall to 1.7 units, due to a huge increase in hydrogen ion, 500,000 times larger than the baseline value. To balance the increase in hydrogen ion concentration, part of the total amount of hydrogen ions will combine to an identical amount of bicarbonate, yielding an increase in the indissociate carbonic acid concentration by that same amount. Solving for X, you will observe a decrease in bicarbonate concentration by 20 milliequivalents per liter, an increase in carbonic acid concentration by 20 milliequivalents per liter, and a final concentration of hydrogen ion of around 4,000 nanoequivalents per liter. This arrangement warrants the carbonic acid dissociation constant, and blunts the pH descent at 5.4 units. On the other hand, the anion gap will now include the unmeasured anion B from the strong acid, rising up to 30 milliequivalents per liter. However, to such a level of carbonic acid concentration, will then correspond a proportionally elevated level of partial pressure of carbon dioxide. So, a respiratory activation must take over, to lower the latter and further buffer the pH. Applying the Winter's formula for the estimation of the final partial pressure of carbon dioxide for the given level of bicarbonate concentration, i.e., 4.1 milliequivalents per liter, 98% of carbon dioxide has to be breathed out, in order to reach a final partial pressure of carbon dioxide of 14 millimeters of mercury. This will in turn activate the carbonic acid bicarbonate system buffer, to warrant the carbonic acid dissociation constant, at equilibrium. So, a negligible 4,000 nanoequivalents per liter decrease in bicarbonate and increase in carbonic acid concentrations, will go unnoticed, while a reduction by 4,000 nanoequivalents per liter in hydrogen ion concentration, will yield a detectable rise in pH, that will eventually stabilize at 7.1 units. Let's move to the second scenario, in which an identical reduction of bicarbonate concentration, will now be due to loss, from the kidneys or the bowel. Here, the loss of bicarbonate yields a reduction of bicarbonate concentration, to 4.1 milliequivalents per liter. Again, in order to warrant the carbonic acid dissociation constant, the concentration of both hydrogen ions and bicarbonate, will rise by around 195 nanoequivalents per liter, while the concentration of carbonic acid will lower by that same amount. Thus, there will be such a small variation in bicarbonate and carbonic acid concentrations as compared to their respective baseline concentration, that it'll go unnoticed. On the other hand, the variation in hydrogen ion concentration will significantly affect the pH, yielding a reduction in its level to 6.6 units. Furthermore, the loss of negative charges due to bicarbonate loss, will now be offset by an identical increase in chloride ion concentration, thanks to the kidneys, leaving the anion gap unchanged. The activation of the respiratory system, as a compensatory mechanism to metabolic acidosis, follows the same rule as seen before. So, for a final bicarbonate concentration of 4.1 milliequivalents per liter, the partial pressure of carbon dioxide has to be reduced to 14 millimeters of mercury. And to this end, a 65% of carbon dioxide has to be breathed out. At that point, the carbonic acid bicarbonate system buffer activates, yielding a reduction in hydrogen ion concentration by 151 nanoequivalents per liter, which ultimately increases the pH to 7.1 units. To conclude, when applying the same rules for compensation in either scenario, i.e., bicarbonate consumption or bicarbonate loss, the paths to the same finish line are remarkably different. And the respiratory system seems to be more exploited when metabolic acidosis is due to bicarbonate consumption.